Welcome back. So let's talk about seismic waves. These are the ripples of energy radiating throughout the earth that we feel. And this is the cause of the earthquakes or the ground trembling. It's caused by these seismic waves. So to detect these seismic waves, we use an instrument called a seismograph. You may have seen these images, pictures of these things, or in movies, something like that. It's that little machine that scribbles on a piece of paper back and forth when the earthquake is occurring. The bigger the scribbles, the bigger the earthquake. Well, historically, that's kind of how they work. When the ground shakes, the little scribble kind of goes back and forth. Nowadays, they're all digital, but historically, what you see here is kind of how they're set up. In fact, in reality, the old school ones, the drawing mechanism actually stays still, but the whole bracket, the whole thing underneath it is what's moving, causing those scribbles. But in any case, nowadays they're digital, but a seismograph is what detects and measures seismic waves. So when an earthquake occurs, at the focus of the earthquake, along the fault where there's break and movement of the Earth's crust below the surface, that's the focus of the earthquake where it occurs. When that rupture at the fault and movement occurs, energy is radiated throughout the Earth in the form of seismic waves. Now, there's two types of seismic waves, body waves and surface waves. Well, body waves, guess what? They travel through the body, the interior of the Earth, whereas surface waves travel along the surface of the Earth. For this class, we'll mostly be talking about body waves, which there's a couple of different main ones, S waves and P waves. Understanding earthquakes can really be boiled down to just understanding the waves, body waves as they travel through the earth. Surface waves, we won't really touch on too much. Let's see here. So as far as the body waves are concerned, we have, again, the P waves and the S waves. P waves stand for primary waves, or first, primary being first. This is in a type of wave called a compressional wave. This type of seismic wave energy kind of compresses the earth, and that compression kind of just travels through the earth, pushes this part of the earth, which pushes this part of the earth, which pushes that part of the earth, which pushes that part of the earth. They arrive first because they are the fastest. The P waves versus S waves. P waves are faster just by the nature of the physics of compressional waves. Again, it's an alternating pulses of compressions and expansions, compressions, expansion, compression, expansion. That's a compressional wave. These can pass through any medium, including solids and liquids. So P waves, or primary waves, can travel through all layers of the earth. The solid crust, the mostly solid mantle, the liquid outer core, and the solid inner core. That becomes important in a little bit. But then you have the secondary waves, or the S waves. They're called secondary because they're slower, so they arrive second. They're the second type of body wave to arrive. Also known as a shear wave. So instead of a compressional wave like the P waves, secondary waves act more like, kind of what you think waves would look like or feel like. Kind of like, roller coaster undulations. That's known as a shear wave. When secondary waves radiate through the earth, it's not so much a compression the material's feeling, but again, that side-to-side kind of more typical wave motion is what is caused by these secondary S waves, shear waves. So more side-to-side or kind of rolling up and down. The big thing with these types of body waves, the S waves, is they only travel through solids, so only through the crust, only through the mantle. They cannot travel through liquid, so they cannot travel through the liquid outer core, nor can they reach the solid inner core because they can't travel through liquid. That's just by the sheer physics of how shear waves work. All right. When these S waves reach a location, they actually do cause more damage. So let me give you a little preview of what these waves look like. I'm going to use a slinky to help illustrate that. So I'm going to just pause very quickly, and I'm going to set up a demonstration to kind of show you how that energy propagating through the earth looks with these primary P waves as a compression or these secondary S waves as a shear kind of side-to-side wave. So I'm going to pause here for just a second, and when this video starts again, we'll talk about that. All right, welcome back. So let me show you the difference between a compressional P wave, a primary P wave, which is a compressional wave, and a secondary S wave, which is a shear wave. So with a compressional wave, like primary or P waves, it's a compression of the Earth's material. And you can see that compression travel through the slinky. You can see the compression travel its way down the slinky and back. So you see that compression going back and forth. Just by the sheer physics and going through the different Earth layers, again, the physics of it, that means it's a faster wave and it gets there first, hence a primary wave. It gets its name, P wave, and that is a compressional wave. Now we have the secondary wave, which is a shear wave, which is like a side to side or up and down motion. So it's kind of, this. So you can see, like this motion in itself, how there's much more movement. So because of this much more movement, this is why secondary waves, S waves, are much more destructive once they travel through the Earth and get to the location. Whether they're just traveling straight up to the epicenter of the earthquake or actually radiating through a good portion of the Earth. But once a secondary wave hits, again it's slower, so it gets there second. But because it is a shear wave, just by the motion of it, it causes much more movement, therefore much more damage and destruction. So we'll pause here and we'll pick up the lecture in just a second. And we're back. So here's a diagram of what we just saw. So again, a P wave, the primary wave, a compressional wave. You can see these compressions and they travel through the medium, and they can travel through solids, they can travel through liquids. And then secondary wave, S wave, is also a shear wave. So that kind of undulating, kind of what you more think of when you think of waves, is what the secondary wave kind of does to the Earth as it travels through. So those are body waves. And again, to understand the dynamics of earthquakes and how they work, it's really just understanding body waves. Once those body waves get to the surface, they turn into surface waves, but from there it gets a little weird. So surface waves, there's two types: love waves, Rayleigh waves. Other than with talking about that, we really won't talk about surface waves anymore, because again, to study earthquakes, it's really just an understanding of body waves, P waves versus S waves, their motions, compressional versus more of a shear motion. And so that's what we'll focus on when we get into the lab as well. On a seismograph, that's the scribbles. This is an image of kind of those scribbles caused by a seismograph. So this is called a seismogram, excuse me. And we can see the different waves on these scribbles. So we have nothing, 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 and then all of a sudden, when an earthquake is able to be read on the seismograph, the P waves are the first ones to get there. The P waves are a more gentler type of seismic waves, and we can see the S waves because again they cause more shaking, more energy, more destruction. So you get the bigger scribbles. So you get the S waves coming secondary. Now, it's our ability to kind of figure out the time differences between when the P wave and the S wave arrived, how much time it took. We can also measure something called the amplitude, which is the highest peak of the S wave, measured in millimeters on these seismograms that help us to later infer the size of the earthquake, assigning the earthquake a particular value on a scale to indicate how big the earthquake was, how much energy was released. That's also known as the Richter magnitude scale. And again, something we'll talk about a little bit in lecture, but definitely touch on in lab. So let me give you another piece of the super secret code. That is going to be the number 4. Okay, you got that? It's the number 4. All right. Number 4. Okay, so we're going to go ahead and pause there. When we come back, we'll talk about some of the hazards associated with earthquakes. I'll see you back here in just a second.